We're going to idea some inverse functions. Like the whole idea of what we're talking about is something like, right, if you want to know what something is in Celsius, right, you just take 5/9 of its temperature in Fahrenheit minus 32. If you want to know what something is in Fahrenheit, you take 9/5 its value in Celsius plus 32. Okay. If your internet dies, Kinley, and you can't watch the lecture, just let me know. I can still give you points for showing up, okay? So, what do we have right here? These are two functions. Spoiler alert, these are going to be what we call inverse functions. Oh yeah, this is part of the lesson, all right. All right. So, right, if I asked you, right, let's call this a function f of c, and call this a function c of f. Right, if I asked you, what is f of c of 0? This is function composition. Remember function compositions. Okay? Well, this means, right, f of c of 0. Remember, this right here is the temperature in Fahrenheit, c of f. The thing on the inside of the c function is f. This is a function in Fahrenheit. And then it's going to spit out a value c, which is something in Celsius, and then we plug that into the Fahrenheit function, and it turns back to Fahrenheit. So really what I'm kind of confusingly trying to say is that if we have function composition of the Fahrenheit and Celsius functions, we convert it to Celsius and back to Fahrenheit. If you convert something to Celsius and back to Fahrenheit, you should get back whatever you started with, right? So it should still be 0 degrees Fahrenheit. And we could do that out and show that it's true. And that's the whole idea of inverse functions, is that inverse functions undo things. So that's the sort of scuffed introduction, but let's get into a definition. All right. Definition. This is a huge definition, so I hope you're ready to learn. Why does my finger look red? It's not red. It looks red. My finger looks like it's dying. I guess I am a ghost today. Oh well. So definition. If f is 1-to-1, remember what 1-to-1 means? Horizontal line test. So if f is 1-to-1, then it has an inverse, and we call that inverse f inverse. This is pronounced f inverse. And by the way, that's not a negative exponent. It looks like a negative exponent, but it's not. It's just the notation that someone decided would be a good idea. All right. Gabe, are you following this? So this is what we're going to be talking about, and this is the notation. All right. And now there's a ton of extra definitions along with this. Okay. F of f inverse of x is equal to x. And, of course, well, maybe not of course, f inverse of f of x equals x. So let's unpack this real quick. Let's talk about this real quick. Function composition of a function and its inverse, they cancel each other out, right? If these are inverses of each other, if they cancel each other out, what's left? Just an x. So anything you plug into the function composition of a function and its inverse, you get back out. Whatever you plug in, you get back out for this new function. In fact, if you remember your exam, there was we actually talked about function inverses right there. In fact, I think I have my exam solutions right here. Yeah, it was problem 11. You remember this? Find f of g of x, where g was square root of x minus 2, and f was x squared plus 2. And when we did the function composition here, what happened? Oh, look at that. When we did the function composition, we just got back x. That's what we're going to be doing today. You already did some of this in number 11 on your exam. We're going to be doing a little bit more of it now. Okay, so a little good news for all of you. All right, and that's what this is. If you do any function composition on a function and its inverse, it should just cancel back out. Just like, right, if I convert something from Celsius to Fahrenheit and then Fahrenheit to Celsius, I should get back what I started with. All right, so that's the idea. So there's another way of thinking about functions and their inverses, and that's of switching x's and y's. So with that in mind, right, the domain of f is the range of f inverse. And likewise, the range of f is the domain of f inverse. Okay? So the whole idea of a function inverse is like flipping its inputs and its outputs, flipping the x's and the y's. And look, you can almost read what's written right behind me, because it's ghost day. Okay. So let's think about this. Again, you can think about it as switching x's and y's. And if you think about inverses as switching x's and y's, then these 2 points make sense, right? Because domain is just all the x's. Range is just all the y's. So the x's of f are the y's of f inverse. Inverse is like undoing. So let's get into an example, shall we? Example 1. I promise we don't have as many examples in the last section. So if f of 2 equals 4 and f of 5 equals 12, what are some inputs and outputs for f inverse? Okay, so what I'm asking is f inverse of what equals what? And the idea here is, right, remember that's whatever's on the inside of the function is like your x. Whatever's on the outside of the function is like your y. So if you plug in 2 and you get out 4 for the function, the inverse is going to go backwards, where you're putting in the y and you're getting out the x. That's how inverse functions work. You switch the x's and the y's. So f inverse of 4 is going to give you 2. Okay. F inverses usually take in y's and output the x's. They go backwards, undoing. All right. And so likewise, we can also do the other thing over here. F inverse of 12 is going to equal 5. All right. So these are our answers. And again, we can kind of check what we think about it, right? One way to check our answers is that we know that f of f inverse of x should be equal to x. So let's check. F of f inverse of 4. What is that? Well, it's going to be f of f inverse of 4. We said f inverse of 4, right? We said f inverse of 4 was 2. Well, what's f of 2? We said f of 2 is 4. So notice, it's like the f of f inverse cancel each other out and we get 4 equals 4. That's how inverses work. They undo each other. So it's kind of how we can, one way that we can gut check and make sure that we're doing this right. Any questions so far? Okay. If there are no questions, let's do a little bit of review. A little bit of throwback to exam 1. Just plugging them in, yeah. Function composition is going to be huge here, Gabe. Welcome back, Kinley. This is just like review almost. This is just like stuff we've done before almost. Watch example 2. Example 2 is really going to be familiar. All right, check. If f and g are inverses. And note, you need to check f of f inverse and f inverse of f. You need to check both directions. No, watch this. You're going to be excited when you see example 2, Lexi. For sure, you're going to be excited. All right. If you didn't like the stuff we did before, it's like I think it's like vegetables that you don't like. Some people don't like vegetables, but if you just feed them garbage food, like completely trash tasting food, then they start liking vegetables. It's the same with math. You might not like function composition 3.4, but by the time we're into logarithms, you're gonna love function composition compared to the logarithms. That sounded like a threat. But it's okay. It's okay. All right. So let's do part A. F of x equals 1 over x plus 2. And g of x equals 1 over x minus 2. We can tie in a little bit of review here. Let's tie in a little review. Let's tie in a little function transformations. Remember, we have a toolkit function of 1 over x. We have a plus 2 on the inside of the fraction, right? It's not over here. It's in the fraction. We have a plus 2. So if we have a plus 2 on the inside of a function, remember that moves it to the left 2 units. Over here, we also have a reciprocal function with a minus 2 outside of the function. Outside of the function means vertical stuff. Minus 2 means g is going down 2. Okay, so just a little bit of review. Reciprocal function left 2, reciprocal function down 2. And we're going to see if they're inverse functions. So we have a surprise for all of you. But I'm not going to spoil the surprise, but there's going to be a surprise. And you're going to, when you see the surprise in this example, you're going to go, whoa, that caught me off guard. I'm sure happier now. All right, so let's check. We need to check f of g of x, and we need to check g of f of x. And remember our definition, it's an inverse function if their function composition equals just x. Okay, so we just go along and say, okay, well, let's see. We already did this. This is 3.4. This is easy. So you say f of g of x. And then we start on the inside and work our way out. What is g of x? It's 1 over x minus 2. And remember when I said function composition is important and you're going to need to be comfortable doing it? I was not lying. So we need to now evaluate this, which is plugging in 1 over x minus 2 into the function f. So what is the function f? The function f is 1 over something plus 2. Where that something is whatever we're plugging in. If we had f of 2, we'd plug in a 2 right here. If we were looking at f of 0, we'd plug in a 0 right here. But we're plugging in this whole mess. So this whole mess needs to go right there. 1 over x minus 2. And this is the big step that you need to be comfortable with for function composition. And if you're not, feel free to ask about how this is working, what's going on. If you're lost, feel free to chime in. The more feedback I get from you guys on how you're doing, the easier it is for me to, I think, address and help you. Okay? Then we're going to do something similar with this thing over here. And we'll also still simplify this left. thing. Are you asking why we don't have parentheses right here, Bella? If so, we could. We could have parentheses there. And I usually put them there. So yeah, that's a good question. You don't need them here, but it's a good idea to have them, honestly. So yeah, let's keep them. But now we're going to get rid of them in the next step, though, because parentheses are only necessary. I like using them, but they're only necessary when things are like being multiplied or divided and stuff. But we're just adding 2, so we can just drop them right here. So we have a -2 and a +2, which cancel each other out. And we're just left with 1 divided by 1 over x. Good question, Lane. So it has to do with what's f and what's g. So f is 1 over x plus 2. So here we're using f, 1 over x plus 2. G is the -2, which is 1 over x minus 2 like this. And that part goes in for the x part. So there's 2 things that do look similar. One of them has a plus, one of them has a minus. And it's the f with the plus and the g with the minus. Good question. And we're almost done. Because this is the reciprocal of a reciprocal. There's a lot of ways to simplify this complex fraction, just like we did in Math 930. A lot of different ways to do it. But we can think about this as the numerator divided by the numerator. The numerator, and I want some cookies. Right? The numerator is 1 divided by the denominator, which is 1 over x. That's one way of thinking about complex fractions. And then keep it, change it, flip it. Anything divided by 1 is just itself, so we don't even need the divided by 1. What is 1 times x? Boom! Whoa! Hooray! Wait, hold on. I just got an idea. I just got a really good idea that you guys will be very happy about. I think I need to incorporate this into my lectures more. I hope it's not too loud, though. What if I played that sound effect at the end of every... Well, we're not done with the problem, but doesn't that make you happy? Isn't that how you feel inside? We got back an x just like we wanted. And now we need to do it again. Okay. We checked one direction, now we need to check the other. So, we do the same thing. This is g of f of x. All right. Could also have like a second one for things if you guys don't like it. But now we need to check the other direction. So we just start on the inside. What is f? F is 1 over x plus 2. So replace it. F of x is literally the same thing as 1 over x plus 2. I'm pointing to something you can't see. So since they are literally equal to each other, they are literally the same, we just replace it with what it equals. And now things are going to get fun again. If they weren't fun enough already, they're getting fun again. We got more complex fractions because we need to plug this into f. Sorry, plug this into g. So what is g, right? G is 1 over something minus 2. But we're not plugging in x down here. We're plugging in this whole inside. So it becomes 1 over x plus 2 is what goes inside. And again, we've got another complex fraction. How do you feel about complex fractions? Well, don't worry. Because the more and more we do with them, the better you're going to get. All right? And no, I don't think all of you sound like children, but I thought it would be much funnier to use a child sound effect. Maybe not, though. I don't know. Is there a good clip of it with adults? Yeah, that's gonna be more accurate. All right. So let's finish the problem. Again, we have the reciprocal of a reciprocal. It's just going to be x plus 2. But remember what we have right here. It sounds angry. Yeah, sometimes you guys sound angry when I talk about math too. Maybe that one's perfect. So, right, this is 1 divided by this fraction. 1 divided by 1 over x plus 2. All right. And then we have a minus 2 below. Order of operations, remember. We have to deal with the division before we can deal with the subtraction. So division is keep it, change it, flip it. And again, multiplying by 1, dividing by 1, neither of those things do anything. This is just x plus 2 minus 2. Which again is just x exactly like we wanted. Yeah, great. Okay. I'm glad we have everything taken care of. All right. So what do we do? We showed that f composed with g of x is just x. We showed g composed with f of x is also x. So therefore, f and g are inverses of each other. And we've finished part A. All right? So again, this is a whole example 2, and it took a little while. All of example 2, this is stuff that was already on your exam, okay? That a lot of you did very well on this problem, which I was surprised. Is it bad to say I was surprised that people did well on this, or is that a good thing? I don't know. But I was happy that people did well on this problem on the exam, and it's just more of this. Just check f of g, just check g of f, and see if it becomes x. All right? So, this is a good time to take attendance for today. So if you are here, someone give me an idea. Someone give me an idea of what the attendance thing should be for today. I'm running out of ideas. I'm going to pull up some more sound effects. We need a good attendance question today. Who would win, a bear or a tiger? Great. That's a perfect attendance question for today. So you need to let me know who would win in a fight, a bear or a tiger, for your attendance points for today. Send it to me on Discord, all right? That's going to be a good one too. We'll use that one. All right. That's the attendance question for today, Gabe. So you have to send the answer, bear or tiger, through Discord to get attendance points for today. And we're going to go on to example B. All right. We need to check whether f of x equals x cubed and g of x equals 1/3 x are inverse functions. All right. So we're going to do the same thing before. We're going to say, okay, what is f of g of x? Hopefully it equals x. What is g of f of x? Hopefully it also equals x. We have to check 2 things. All right. Oh no, Lane, what have you done? All right. So we're going to check both directions and see what happens. All right. So f of g of x, what does that equal to? Well, we just take f of g of x. This is just the definition of f of g of x. Start with the inside. G of x is 1/3 x, so we just replace the g of x with the 1/3 x. Okay. And then this gets plugged into f. F says you have something cubed. If it's f of x, it's just fx cubed. All right. But this is not f of x, this is f of 1/3 x. So it becomes 1/3 x cubed. Oh no. Look what happens. When you cube a monomial, you cube the coefficient and the variable. This becomes 1/27, because that's 1/3 cubed, times x cubed. Right, that's not x. That's not x. So we know that this is indeed not an inverse function. We don't even have to check this anymore, right? Don't have to check. Because we already know the answer. Okay? So we already showed that they're not inverse functions. We don't need to show it again. Right? It's like to prove something, you have to prove it always. But to disprove something, you only have to disprove it once. That kind of a deal. You guys like? Anyone want to give me a nice reaction for this nice pun? Anybody? All right. All right. Thanks, Lane. I appreciate that. So that's example 2. All right. So let's keep going. So something else, if you want to find the inverse function, because these weren't inverses, you might say, well, I wonder what the inverses actually were. Yeah, I think that would have been better, Gabe. Next time. So to find the inverse function, again, if it exists, of y equals some f of x, just replace the x's with y's and solve for your new y. I'll switch. Let's say switch instead of replace. It's a little bit easier. Okay. And this is where things get really fun. You can really see whether you're an algebra master. You can prove to yourself that you are so skilled at algebra, okay, and solving equations, because some of these can be kind of tricky. All right. So let's get into this example. Ejemplo 3. What are the inverses? What are the inverses, if they exist, because they're not always going to, of the following? We're going to go through all of our toolkit functions. So again, a little bit more review for the quiz today, implicit review. Okay, so we're going to make a table, and we'll fill in the table, and we'll do the problems off on the side. So function inverse. All right. So really quickly, we have back to back included this little parenthetical. If it exists, if they exist. Remember back to the definition, which I will show you. How do we know if something has an inverse? If f is 1-to-1, then it has an inverse. So this is the big condition we need to check. Remember to check whether something's 1-to-1. Horizontal line test. All right. So let's just start talking about all this, and we'll use some horizontal line tests, and we will see whether these functions have inverses. All right. So start with the first one. The first function we talked about was the constant function. This is one of our toolkit functions. Okay? Specifically, the constant function is a flat line. So if you're wondering whether a flat line passes the horizontal line test, one or no longer, you could graph it if you really want to see it. It literally could not fail the horizontal line test any harder, right? If you use a horizontal line test, it is the function. It is a horizontal line. It definitely fails. This is not one-to-one. There is no inverse. You might say DNE does not exist. This is very, very much not a one-to-one function. Another toolkit function we did was y equals x. Okay, that was called the identity function. Looks like this, I'm reversed. A nice diagonal line. Well, this passes the horizontal line test, right? Use a horizontal line test everywhere. So let's find the inverse function. So to find the inverse function, if it exists, switch the y's and the x's and solve for y. Well, if we switch the y's and the x's, what do we get here? We switch the y's and the x's, we get x equals y. Right? Switch the y's and the x's, and this is what you get. This is itself. The inverse function of y equals x is actually just y equals x. Okay? Let's do some more ones. How about y equals x cubed? This is a good one. Switch the x's and the y's. What do we get? We get x equals y squared. Did I say cubed? I meant squared. Y equals x squared. So switch the x's and the y's, and this is going to be our inverse function if we solve for y. But remember, we already know this is not going to be a function. Right? Remember back to when we started talking about chapter 3. We said, if you have y squareds, it's not going to be a function because you're going to get two things for every x. But let's say you forgot that. We take the square root to solve for y. We take the square root of both sides, right? And we take the square root of both sides, we get this, and that's not a function. Okay, so this does not have an inverse function. Equivalently, right, if we just look at y equals x squared, whoa. That's the wrong function. This is a very interesting function, actually, x to the x, but we are not going to be talking about it in this class. This is a funny looking one. This is what we're going to talk about. X squared, right? It fails the horizontal line test. It's not one-to-one. So we know x squared doesn't have. All right, so we can go through these a little faster. All right, y equals, what's next? X cubed. This x cubed, remember, is one-to-one. It goes like, reversed. So it looks like you just switch the x's and the y's to find the inverse function. X equals y cubed. Take the cubed root of both sides. You get y equals the cubed root of x. All right. This is a good review for today, though. And remember, we showed this, actually. We showed this before, this relationship between these two graphs. All right, let's look at 1 over x. 1 over x, we don't talk about this toolkit function that much. So this is good review. 1 over x is the reciprocal function. And it looks like this. Oh, I know people that enjoy things way weirder than this. People have very strange likes and dislikes, let me tell you. And that conversation can be taken down very many interesting avenues. Okay, so this is one-to-one. It's almost not one-to-one, but this is never in line with this. Okay, So it is 1 to 1, and we can solve its inverse function. Okay? So let's get inverse functioning, shall we? So again, you can go off to the side somewhere and say, to find the inverse function, we need to switch the x's and the y's, and solve for y. Don't forget 930. 930 is important. Do not forget it. How did we solve rational equations? We multiplied by the LCD. Multiply this side by y and this side by y. So we get xy equals these cancel is 1. And then to solve for y, we just divide both sides by x. Y is 1 over x. And look at that. You can see it through my head. I just give it a little pink flare. Okay. So the inverse function of y over x is, again, also 1 over x. Sorry, 1 over x, not y over x. All right. And you can keep on doing this. All right. There's some more identity functions, but we're going to move on for time purposes. We can do a couple more examples. I think we'll have about 10 minutes left to review for the quiz. All right. So we are zooming today. Do some more good inverse problems. All right, so example 4. The domain of f is the interval 1 to infinity, and the range is the interval negative infinity to negative 2. Question is, find the domain and range of f inverse. So I postulate that this is an easy problem, okay? As long as you know how to do it. That's like math in a nutshell, right? If you don't know how to do it, it's not easy. Kind of a tautology. Anyway, go back to your definitions. Remember back to our definitions at the very beginning of today. The domain of f is the range of f inverse. The range of f is the domain of f inverse. So all you do is switch the x's and the y's to get to f inverse, right? So the domain of f inverse is the x's of f inverse. That's going to be the y's, or the range of f. So it's just negative infinity to negative 2. All right? And likewise, the range of the inverse function is the domain of the other one. So it's 1 to infinity. That's all there is to it. Because remember, just like before, remember the previous example, what we just did. What we just did, right, to find the inverse functions, we switch the x's and the y's. That's one of the big things for inverse functions. Switch x's and y's. And domain is really just x's. Range is really just y's, right? All right. So again, this is the end of chapter 7. We haven't finished yet. Chapter 7. 3.7 is the end of chapter 3. If you're thinking, man, I can't wait to be done with functions. Well, first off, you're kind of screwed because 1400 has a ton of functions. But once we go to chapter 5, we're skipping chapter 4. Once we go to chapter 5, it's going to be a lot less functiony. Chapter 5 is going to be fun. 5.1, by the way, which we're starting tomorrow, is going to be on quadratic functions. And you might say, quadratic functions, Jason, that sounds easy. That's just review. We've talked a lot about quadratic functions. There's going to be some new stuff tomorrow, but it's a fun section. I love tomorrow's section. I won't call it review though. If I call it review, you guys are going to call me liars. All right, but tomorrow should be a good section. So here we go. Let's move on to example 5. Below is a table showing the distance f of t traveled in t miles. What? Sorry, traveled in miles after t minutes. Find f inverse of 70. So the table is going to have t and f of t. We love tables in this class. 30, 50, 70. I think a lot of you guys like tables too. Because when I asked for furniture for the extra credit question, a lot of people chose tables as a furniture, which I really think was your subtle way of saying, Jason, I like tables so much when we do tables in math class. Let's do more tables in math class, I think. All right? It's a possibility anyway. So it is what it is. So again, let's think about what this table means. Again, reviewing what functions mean. F of t is a function that if you give me a time, I give you f of t, which is the total miles traveled. So after 30 minutes, you've gone 20 miles. After 50 minutes, you've gone 40 miles. After 70 minutes, you've gone 60 miles. After 90 minutes, you've gone 70 miles. Okay? So we just have to look at the F inverse. Okay? I can't think of that, by the way, without, I don't know if we have any Star Wars fans here, but...
You assume too much. You assume too much.
That stupid guy from episode 1 in Star Wars. That was a little loud, I'm sorry, but that's what it made me think of. All right, so let's solve this. Remember, what do we have here? F inverse of 70 is going to equal, right? This is like the y. Most functions, what's inside here is like an x. But remember, for inverse functions, we put in the y and get out the x. I'm just very good at Googling, Monet. Surreptitiously Googling while I'm trying to talk and make it seem like I'm not just focusing on finding clips of Star Wars videos. All right. So this is the y. Well, so we scout our y column. We get 70. We need to find the x column. That's 90. All right, so F inverse of 70 is equal to 90. Right? This is the miles. And this is the time. Okay? I got to admit, it's a lot easier to meme teaching online. Okay. Because remember, f of t, over here the inside is the time and the outside's the miles. But inverses have it flipped, where the inside's the miles, the outside's the t. All right. Let's do one more problem, and then we're going to review for the quiz. All right? We're almost done with the whole section. We could finish the whole section today, but we don't need to finish the whole section today. And if we're doing good on time, I think it would be helpful to review, because your quiz today is going to be it's going to be a quiz. All right. Let's go. Example 6, last example of the day. All right. Well, if it's the last example of the day, let's do it on the next page so I can make sure it all fits together. E's don't have 4 horizontal lines in them. That's not how that letter works. Okay. Consider the graph. Of G, shown below. All right, I'm going to give you this nice graph. It's going to go up to 8. So when x is 0, y is 1. When x is 1, y is 2. When x is 2, y is 4. And you might say, oh, this is a parabola. But don't worry, it's not. When x is 3, y is 8. When x is -1, we are at a half, and then a quarter, and then an eighth, and then we get really, really close. And this is our function g of x. This is a function that many people are aware of right now. An exponential function, which is a little taste of what's to come in chapter 6. That's when we really start getting into talking about exponential and logarithmic functions. But hold your horses. It doesn't matter. They just deal with an exponential function. You don't need to know about exponential functions to be able to read this graph. So I've got some questions for you. Find g of 0. So remember, this is saying this is our x value, and we need to know what's the y value for g. All right, so someone tell me, what is g of 0? All right. Yeah, exactly, Monet. Exactly, Gabe. Yeah, the kids are excited. All right. So we just went x is 0. What is y? Y is 1 here. So that's going to be our y. Okay. And if we were talking about g inverse of 0, it would not exist. Yeah, because y will never be 0. So likewise, let's go on to part B. Okay. Don't forget about Lexi. Lexi, you do a good job so often that sometimes I forget to compliment you for it because it's just so normal. That's supposed to be a compliment. It sounds like I'm throwing shade at Gabe and Monet. Oh dear. I'm just trying to dig myself out of a hole for not having seen your comment, but I think I'm digging a bigger one. Fun fact, I actually really like digging holes at the beach. Growing up, a lot of times when we went to the beach, because I grew up in California, I would just dig big holes with sand. I don't know why I enjoyed that, but I did. Okay. All right, let's go on. Find f inverse. Hold on. We got the wrong letters over here. Find g inverse of 1. So again, for a normal function, you plug in the x and you get out the y. But here you can think about this as like what is the y for g? And then we need to find the x. So when y is 1, what is the x value going to be? Yeah, exactly, 0. All right, we're just going backwards from what we had over here. We said g of 0 is 1. That means g inverse of 1 is 0. So a lot of times they might come in pairs. Okay, so let's do a harder one. What about g inverse of 4? What is g? So again, to find g of 4, you would find the x, 4, and then find the y, which is way too big. But this is asking what is g inverse of 4? Okay. Any ideas? Two or three, and it really depends on how well I drew my graph. It's supposed to be 2. When the y value is 4, the x value is 2. So it's supposed to be 2. All right. Because when the x value is 3, the y value is like 8. But yeah, it's easier to tell when I draw good graphs. All right. And that's it. We only have 2 more examples tomorrow, and they're not that bad. Really, they're not that bad. I mean, I don't think tomorrow's examples are that bad. Let's review real quick for the quiz today. Okay. So I'm gonna pull up, because remember, your quiz problems are just taken from the book. Your quiz today is going to be on transformations of functions. Okay, so I got something in my eye. So you can just go see what your quiz is going to look like. It's going to look like some problems from this section. All right, so let's look at the first group of problems. Write a formula for the function obtained when the graph is shifted as described. So something like this, if it's shifted up 1 unit and to left 2. Remember, vertical stuff is on the... I'm glad you guys could not smell that. You only had to hear it. I apologize. That was disgusting. Vertical stuff is on the outside of the function. So like it would be in front or behind the square root, but not inside the square root. So we're going to add a +1 on the outside. Horizontal stuff is on the inside of the function, so on the inside of the square root, on the inside of the absolute value. In the denominator of the reciprocal function is horizontal stuff. And to the left 2, remember we're not going to be subtracting 2 on the inside because horizontal stuff is kind of backwards. It's going to be adding a 2. So for something like this, right, 3.5, review, for something like the square root of x up 1, left 2, it's going to become square root up 1 means add 1 on the outside. Left 2 means add 2 on the inside because it goes backwards from what you might expect for horizontal stuff. All right, and that's something like the first group of problems. I'm just going through these pretty quickly as review, but if you have follow-up questions, you need to interrupt me, okay? So let's look at the next chunk of problems, right? How the graph is a function transformation. So this one, it's on the inside of the function, so it has to be horizontal. And it's kind of backwards from what you might expect, so it's going to be 49 to the right. Inside, 43 to the left. 3 to the left. 4 to the right. These first 4 are all horizontal shifts. These ones are on the outside of the function, so you know it's going to be something vertical. Up 5, up 8, down 2, down 7. And then you could combine them too. We skipped these. I actually don't remember whether I assigned these, but these ones aren't going to be on the quiz. I think I did assign these actually. Yeah, so to sketch each transformation, all you would do is identify the transformation. So up 1, down 3, or right 1. And then just move all the points that direction and draw the same shape. Okay. Again, this one sketches. It helps to draw a toolkit function. If you can draw the squared function, a parabola, absolute value function, cubic function, or a square root function, and then write down your transformations, transform them with the tables like we did in class. All right, so make sure I'm doing good on time. All right, so for something like 30, we could do something like this, right? It's m of t equals 3 plus the square root of t plus 2. It can help. It's up to you though, right? How you want to do this. It can help to write your, well, I guess it's t's and m of t right here. This is just going to be a transformation of a square root function. If you remember what a square root function is, it kind of looks like this. Like the square root of 0 is 0, the square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. And this table that we need to graph is just going to be a transformed version of this table, right? So this is going to be left 2 on the inside, and there's a plus 3 on the outside and up 3. So the x values move left, so this becomes negative 2. The y values go up 3. Left 2 becomes negative 1. Up 3 becomes 4. Left 2 becomes 2. Up 3 becomes 5. Left 2 becomes 7. Up 3 becomes 6. So we know the shape from the toolkit function. We know the points from the transformations. Again, or you could just have plugged these t values into m. You could plug these in directly. And then you're just going to essentially I'm not going to spend the whole time doing it, but you're going to get something like that. Okay. And then for these next group of problems, this is very similar to what we already did, just with horizontal tables instead of vertical tables. For these, you need to identify the toolkit function and then identify how it got moved. So this is an absolute value function, the v. This is a parabola, x squared. This is a square root function, square root of x. And then notice that this one got moved to the right 3 and down 2. So how do you write those as function transformations? This one got moved to right 1 and down 3. This one got moved left 3 and down 1. All right, and that's how you approach these couple. And then there's the more complicated function transformations like reflections. This is the square root function that got reflected upside down. So that's a negative on the outside. Upside down is a vertical change. That's why we know it's the negative on the outside. Whereas this got reflected to the left. That's a horizontal change, so it means it's going to be a negative on the inside. All right. And again, now the parabola is going down, so you know there's going to be a negative on the outside. This is flipped, you know, we're going right 2 up 1, and it got flipped upside down. All right. So you need to know what these toolkit functions look like before you actually can figure out what's going on to them. All right. Even, odd, and neither. This is the last thing I want to review. We're not going to get through reviewing the whole section before I want to let you go to your quiz. Remember, even means symmetric with respect to the y-axis. Odd means symmetric with respect to the origin. Right? Even is symmetric with respect to the y-axis. Odd is symmetric with respect to the origin. This is how you do them graphically. But if you want to do them, algebraically, for even, you check, what is f of negative x? Is it equal to f of x? Then it's even. For odd, you check out, what is negative f of negative x? Is it equal to f of x? And that's how you check for odd. Okay? And these are the same because this is a horizontal reflection, which shows symmetry. This is a horizontal and vertical reflection, which shows symmetry for the origin. All right. And that's a crash course and review for the quiz today. Good luck. You can go ahead and get it started now, and should probably grade it afterwards. Please double check when you upload your files that you're uploading actual image files. Sometimes there are bugs and like it uploads just a file called photo that's not actually a photo. Okay. So please check for that. All right, good luck. Bye.